Hi everyone, my name is Ray, and today I will be talking about rowhammer. Rowhammer is a hardware problem, and it's caused by some recent DRAM devices where when you access a specific row repeatedly, sometimes the value in the neighboring rows might flip and cause some unexpected results. And of course, anytime there is unexpected behavior, hackers will flock to it and figure out some way to exploit it. So today, I'm going to try to show you guys some of the basic concepts behind rowhammer and how we might be able to exploit it. First of all, let's take a look at DRAM. DRAM stands for Dynamic Random Access Memory. DRAM is used in your laptops, your phones, your tablets, maybe even your cars. DRAM consists of numerous little cells. Each cell is essentially a capacitor that is capable of storing exactly one bit of data. And these cells are grouped into rows, so when you access DRAM, you're accessing an entire row each time. For each congregation of DRAM, which is called a bank, there's a special row buffer. Whenever a row needs to be accessed, the content of the row is copied into this special row buffer. This is called activating. The active row can then be accessed by the CPU, and it has to be copied back to its original location before another row can be activated. Now here's the catch. Capacitors, as a piece of hardware, are not physically perfect, and they sometimes do leak, thus affecting other capacitors around them. So when a row is repeatedly activated, the current may cause its neighbors to suffer from bit flips. This repeated activation is also referred to as hammering, and this is where the term rowhammer comes from. Now you might be wondering, just how often does this happen exactly? Well, in 2014, a few researchers at CMU did a study on this, and as it turned out, this is surprisingly common among modern DRAM modules. Now we need a way to reliably figure out where those faulty rows are. There are two major steps involved in this. Firstly, we all know that modern computer architecture supports multiple layers of cache for memory access. Data from RAM is put into cache so that when we repeatedly access them, we're interacting with cache instead of RAM. Fortunately for us, there's a tool that we can use to get around it, which doesn't seem to have much use anywhere else, just like everything else we've been abusing in this class. The instruction CLFlush invalidates the cache line that contains the linear address specified, thus effectively allows us to bypass the cache. What's surprising is that this is an unprivileged instruction in the x86 architecture, and it cannot be disabled. I do want to point out that the ARM equivalent is privileged, so this technique only works with the x86 CPUs. The other requirement is that we need two rows that are in the same bank. And the reason is that if we just keep hammering the same row over and over, we're just going to cause the row to be stuck in the row buffer without ever being replaced. However, if we have two rows and we alternate between those two, they're going to take turns being copied in and out of the row buffer for every access. And that's exactly what we want to do for row hammering. However, this may not be so easy due to the fact that on most modern systems, physical memory is mapped into virtual memory, and normally as end users, we don't have any knowledge of physical memory addresses. Well, here's the good news. Most systems have only 8 banks, and if we pick 2 rows at random, there's a 1/8 chance that these 2 rows are in the same bank, which is not bad at all given how fast the operation is. So here's the code as proposed by the CMU researchers that will give us what we want. As you all can see, this is pretty simple and straightforward. We're just reading 2 addresses and flushing them, and we repeat this whole process until something something awesome happens. I'll be showing you guys a quick demo using rowhammer developed by VUSec, which is the cybersecurity department of a university in Netherlands. So they developed this Android application for people to test whether their devices are vulnerable to rowhammer. Feel free to take a look at their source code. It's not supposed to do anything destructive in theory, but make sure you read the disclaimer before you try anything. Okay, so here I have my personal Android phone. It is a Sony Z3 released in 2013, which means there's a very good chance that its DRAM is vulnerable. So I've downloaded this Grammar application as the provided APK, and I've set the aggressiveness to the highest, and now I'm gonna start hammering. So this process is currently running, and it's just going to be testing random addresses, and I have no idea whether it's gonna exit at all or when it's gonna, how long it's gonna take. So either way, I'm just gonna leave it and come back in a little bit and see if we get any result. Okay, well, as I've noticed, the process has stopped, and apparently it did find some flips from my phone, which I don't know if I should be happy about it or not. But I'm gonna take a screenshot of this interface, and we're gonna go through some of this information here. So let's take a look at this log. There's something quite interesting here. First of all, we've noticed that only 3 megabytes of RAM has been hammered, and yet we found 2 exploitable flips. That is quite alarming, given that my phone has a RAM size of 4 gigabytes, which means there could potentially be over 1,000 flips that are exploitable. The other thing is, it took only less than 2 minutes to find the first exploitable flip, which means if someone tries to attack my phone using the rowhammer exploit, they'll be able to break through extremely fast. There is no telling how many different ways this can be exploited, but the fact is the guys behind this app have already released a video showing them rooting an Android phone using rowhammer. Obviously they did not disclose the techniques behind it, but it is something all Android users might want to be concerned with. Besides Android devices, there are a number of other platforms and systems that can be exploited in such a way. Now I will discuss about an exploit called Flip Feng Shui. This exploit allows a virtual machine that runs on some kind of cloud platform to attack its peers that are in the same host. It relies on the behavior of memory duplication engine used by the host, and in particular these two behaviors. First of all, when duplicate pages are detected across different virtual machines, the host will keep only one physical copy, while mapping the virtual memory of both virtual machines to that one physical copy. On top of that, whenever a virtual machine writes to a page that is being shared, the host will make a copy of that page so the write doesn't affect other virtual machines. This is also known as copy on write. Now we carefully craft a 3-stage process to make use of that knowledge. As an attacker, we must first obtain a page that is identical to a page from the victim's memory. Then we wait patiently for the memory deduplication engine to find this duplicate page. The host will then keep only one physical copy of it so that our virtual memory and the victim's virtual memory are both mapped to that one page. Now, if we were to write to the page, the host will make a copy of it so it's no longer shared between us. But instead of writing, we now have the option of causing a bit flip using rowhammer, thus allowing us to modify the page without the memory engine messing it up for us. There are 2 ways this can work to our benefit. The first is through OpenSSH. As we all know, the RSA algorithm requires a public key, which is stored in this file called authorized keys. The key usually is not possible to be factorized, but with a flipped bit, factorization is much easier, and once we have all the factors, we can easily generate a new private key, allowing us to forge the victim's identity. The other weakness we can use is apt-get, which is used as the package manager for Ubuntu. Two files are especially important to apt-get. The first contains a list of domains where apt-get will try to fetch its packages from. So if we were able to flip a bit in this file, for example changing ubuntu.com to ubuntu.com, we can then force apt-get to download the package from ubuntu.com, which I assure you is not malicious at all. Once the package is downloaded, we have the other file that needs to be dealt with. This file contains the list of trusted packages that apt-get is willing to install. And once again, if we can just flip a bit inside that file, we can trick apt-get into installing something that it shouldn't trust at all. Do take note that these exploits are very experimental and they can only be reproduced in highly controlled environment. So this concludes my introduction of rowhammer today. I hope you guys all learned something today, and always make sure you pay attention to where you're downloading your RAM from. Thank you.